right. So if you have, we're going to kind of use the like one page with the chart on it. We're not going to use in class today, but we'll use that for the videos that are posted today. We're going to kind of go through the other little, I guess it's kind of a packet, the stapled together pages. Just to give us a little bit so I can, I guess, write more in your notes and kind of explain some different concepts, hopefully a little bit more clearly than you having to write it all out in your own notes. So what we are thinking about now, and today we're going to start to transition more heavily into some of the, I guess, the theory. And we're going to do that by first doing stuff that we've done before in control volumes. In that context, we're going to take it and say, how does all of those kind of tools in our toolbox, how do we apply those now in systems where we have a control mass? And surprise, surprise, it's basically exactly the same. But it's different enough that there are some kind of nuances that we have to make sure we keep track of so we're not getting, you know, the way we did things for the first, I guess now this is week 10. So for the first 9 weeks, now how do we do things now? It's basically the same, some minor differences. So we'll try to make some special note of what those differences are. And hopefully you find some of these problems, you're like, oh, I've done this before. I know how to do this. So the first thing, we talked a little bit about these early in the course, these first 2 points. So when we have a multi-step process like hopefully you went and solved the last couple homework problems. When we have multi-step processes like this, we can define things either as point functions or path functions. And maybe from that, you already have an idea of what the difference is between a point function and a path function. We sometimes call the point function either a point function or a state function. I don't know, both of them. So a point function, let me just define it. That's going to be something where the value or magnitude depends only on the current state, not how the system arrived there, or how you reached that state. It depends on like where you are now. It doesn't care what the history was. So it has a definite value at a given point. So I'm not very good at definition writing because I called it a point function or a state function, and then I used point and state in the definition of it. So it's a little bit of a circular definition, but hopefully it gives you a picture of what we're talking about. Things that, you know, if I tell you, right, like we've done before, if I tell you 2 things about the system, these are all the other things that you could look up, right? So this is things like temperature, pressure, density, right? The pressure outside today doesn't matter what the pressure was yesterday. The temperature outside, it doesn't, like what the temperature was yesterday has no effect on that. Okay, like if I tell you that this is 50 degrees, it's 50 degrees. It doesn't matter if it's 50 degrees and just cooled down to 50, or if it's 50 degrees and just heated up to 50 degrees, it's 50 degrees, it's 50 degrees, right? So these are things like that. So density, specific volume entropy, internal energy, and you might get I'm just writing down the things that we look up in our tables. Internal energy, enthalpy. And there are a lot of others as well, but these are the ones that we've run into in this class, and these are the kinds of things that we've looked up in tables. Okay, so maybe if that helps you remember, like what kind of things did we look up in tables? Those are point functions. A point function means like we have a point, we called it point 1, and we could write everything down for it. A path function is something where the value or magnitude depends. Again, I'm not very good at writing definitions. Depends on the path followed, as well as the start and stop, or the beginning and the end. The start and stop states. Examples, heat, work. Those would be the two in this class. Again, there are other path functions, but those are the two we run into. Things that, at least if you drew some of the, again, these kind of last couple of problems, if you drew them how I typically draw them, I'll draw like, you know, one thing's over here, and then there's an arrow, and then there's another thing over there. So the start and the stop, those are our point functions. That's like point 1, point 2. How we get from point 1 to point 2, that tells us something about our path functions like heat and work. Okay, so one of the things that you maybe have not noticed, but I can say explicitly now, when we've written the first law, we always write it, it's kind of a weird thing, because conservation of mass, we write like delta mass equals 0. Conservation of energy, we have like some stuff on one side of the equation and some stuff on the other side of the equation, but the real equation is that the change in energy of the whole system is equal to 0. The reason we split it up like that is because we put point functions on one side, internal energy, enthalpy, like kinetic energy, potential energy, those are all point functions. We put those on one side and we put the path functions, heat and work, on the other. So that's why we split it up like that. For a control mass, we're typically going to write, again, it's going to look really close to the same, but not exactly the same. So I'll just write it and then we'll explain the differences. This is what our first law will, in this class, look like. It doesn't have quite as many terms as the first law for a CV. And that's because, right, so for a control volume, we had kinetic energy and potential energy both on the left side. We're going to drop those from the equation. We often did anyway. In control volumes, those were the first things that we crossed out. We didn't always cross them out. Sometimes they stayed around. We're going to always cross them out in control mass problems, not because there's like something fundamental where they are always crossed out all the time. Sometimes they're important. The control mass problems that we're going to deal with are going to be really exclusively like piston and cylinder problems, again, because that's the only way that you can do it, because that's an easy way to think about it when you're first when you're learning some of the kind of theory, which is what we're trying to do. And if you wanted, say, like a change in potential energy in a piston cylinder problem, you're talking about like taking your piston and like throwing it in the air. Similar, like change in kinetic energy, you like throw your piston across the room. So there's just things that aren't going to happen in the analysis of the problems that we care about. It does happen. It does happen in control mass problems where you have changes in kinetic energy and potential energy. If you take fluids, we're going to do control mass problems and we'll do change in kinetic energy and change in potential energy and stuff, because we're going to talk about like looking at a piece of fluid that's moving. So it's going to be, maybe it accelerates, maybe it slows down, maybe it goes up in the air. So you have to take into account all of those things. We're not going to in this class. Again, like the first law is way bigger than any way that we've ever written it. It's all of the kinds of energy that you have. The change in all of those kinds is zero. So like we haven't done nuclear reactors, but if we wanted to model a nuclear reactor core, we would for sure have to take into account more than just like, you know, change in internal energy, kinetic energy, potential energy. You'd have to take in like, right, change in nuclear energy. If there was a chemical reaction, you would have to do chemical energy. If there's electrical energy, you have to take into account that. So this is just like the subset of energy that we happen to care about for the problems that we're looking at. These are the ones that are there. Okay, so that's why we drop kinetic and potential, because we're not throwing things across the room typically. Sometimes you are. Then maybe you have to keep those into consideration. Okay, the other thing that happened, so we dropped kinetic potential. We dropped the little dot. Remember what the dot meant? That was our rate variable, or our rate notation. So that was like a time dependent, like an in and out, time dependent thing. So in control mass problems, we don't have stuff going in and out. We have a process happening and like an initial state and a final state. So we no longer have an in and out. So we no longer have a rate. So we just go to, now they're capital letters. So it's a total amount, the total change in potential, the total change in internal energy equals the total heat minus the total work. So we dropped the dot. Anything else? Oh, last thing, we got a U instead of an H. The biggest change. Why do we have a U instead of an H? So remember, for an H, I'll make this a different color, but right, H was equal to U plus PV. Does anybody remember, like, physically what those two terms are? What physically is U? It's internal energy. What is internal energy? What does that mean? It's the heat energy of stuff. So this is, so U here, that's heat energy. So zoom in so you can see my tiny writing. That's heat energy. Remember what the PV term was? What we called that? Okay. This is flow work. It was quite a long time ago that we actually broke it apart like this. I think it was the second day of class, or the second week of class. So it was a long time ago. And then we kind of just forgot about this and just used H and said H is the energy of the fluid. So that was true, but it was really the energy, so the thermal energy plus the flow work energy. And flow work was, that was the energy that it took to push stuff into the system and to push stuff out of the system. So it was like, if stuff came in, it came in with amount of heat, amount of thermal energy, plus it like came in. So that was a work, a PV term. So when we had a control volume, we always had stuff going in and out. That's why we always had that PV term. In a control mass, we don't ever have stuff coming in and out because we defined our system so that that doesn't happen. Like we're looking at a set amount of stuff. We can't have more stuff come in and out because we're looking at this one set of stuff. So that's where the difference is. The take home is U goes with control mass, H goes with control volume. Okay. So if we look at this, this equation, delta U equals Q minus W, right? One of the things that we can see, internal energy, that was a point function. Heat and work, those were both path functions. So delta U, if we go from any initial state to any final state, it doesn't matter how we get there, delta U is always the same. So in the problems that you calculated for today, you got different values of work. Hopefully you got different values of work for every different problem, despite the fact that you started at the same initial point and ended at the same final point. So that means that, right, delta U was the same because you had the same start, same end. Work was different because you went different ways. That means that Q must also be different because you went different ways. So we're going to spend, if you flip that over, get out your homework. This is kind of a way to just check and make sure that you did your homework right. And just quick do some energy balances. Once you get them, they're super easy. I'm going to find, so this is the exact same problem that you solved, so you don't have to resolve anything for work. Just as a note, I'm going to quick look up what U is at the initial state and the final state, so that you don't have to do that. Because at this point, I trust that you can all do what I'm doing here. Okay, so we were at we're water. No, 250. 250 and 0.3, and then what's our final state? Twice the volume and 400 kilopascals. Does anybody have what the specific volume is of the final state, so I don't have to do the math? 59272. Okay. 1.59272. Yeah. And our pressure was 0.4. Okay, so those are the values that we get. We go from 250. We went from 250 to 1100 Celsius. Right, we went up in pressure but expanded. So the only way to do that is by really cranking up the temperature. Our internal energy went from 2729 to 4272. So this is U1 equals 2729, U2 4272. 4272. So just one thing to remember, when we got really used to looking at H, we have to switch gears and now start looking at U. We use it the same, but we're going to be using U for control mass. So those are both in those are both in kilojoules per kilogram. So spend a few minutes. Once you get the first one, the other ones are super easy. If you had questions about your homework, this is kind of a good spot to make sure that you got all three of those right. Okay, and if you want to check yourself as you go, those are the answers that you should be getting.
Because I put in kilopascals, and I did not do that. Yeah, what do you say?
It's twice the initial. It's like
Yeah, what's the, because I put in like 300 for M, for like megapascals instead of kilopascals.
So you're a big number.
Yeah.
The initial is 0.796.
How are you doing, Brian? Do you know how you?
No, I'm confused.
So your how does the?
So I cut to the W.
Yep.
And
So you're going to use the for the we know U.
yeah.
So we can find delta U. So we have U and W. We're just using those to find Q. Like the energy balance from the previous.
W, I just make sure I got W right. W is just your pressure times your initial volume. Or you change the volume.
Yeah, so it's the picture that you drew, it's the area that you shaded. Yeah, so you can do, you should get 3 different values. It looks like you're 25, but it looks like, yeah, 20, yeah, 23. That's right. Other people got 23.
Yeah.
Did anybody show of hands on the last problem? How many people actually did the integral?
I just did the area of a triangle. Oh.
Did you just do the area?
Yeah.
Did everybody just do the area? Yeah. Nicely done.
Oh.
Yeah, people mostly at least getting started on the first one. I think once you get the first one, then the second 2 are a matter of the moment. Okay, we'll spend maybe 3 or 4 more minutes on this. Okay, so while people are working on that, there I have two, this is apparently a physics demo, two identical steel balls. So we're going to go down. Who will win? Who will win?
I want to say the straight one. I'll say orange just so. Go in there. I'll say the orange.
Why will it win? The straight one has a shorter path to go. What will be, different question, what will be the velocity at the exit? The same or different? Different. Conservation of energy.
Yeah.
Right? So they should be what? The same. Conservation of energy. So there's a change in potential energy. You're converting potential energy to kinetic energy. So you end up with the same velocity. Doesn't matter what happens in between. Kinetic energy is a point function. But this one gets started because the slope is bigger. It goes faster here and then slows down. So we'll see. So orange wins.
Yes.
Orange wins.
Is that just because it starts faster? And it's just way faster.
So it gets through, I mean, it gets to here with the higher velocity and only here starts slowing down, but it slows down here to this one's maximum velocity. So the velocity in the orange is higher the entire way because they exit with the same velocity. Anyway, not my demo, but I kind of wish it was. Did everybody get mostly done, or at least feel like they understand what they're supposed to be doing for that one?
I'm confused how people are getting 23 for the first work.
Okay.
I'm getting 238.
Multiply by 0.1.
Yep. Okay.
Because you're in 238, you're in kilojoules per kilogram.
Okay, thanks.
And for Q, it's just a change in U.
Yeah, so it's
plus
just
W, right?
delta U equals Q minus W. So Q equals delta U plus W. Okay, so just like we had differences in work for different paths, we're also going to have differences in Q for different paths. That's something we didn't totally experience or get into in control volume problems. We did a little bit, but it wasn't maybe this explicit that both work and heat transfer are both path dependent, like how you got from an initial state to a final state. The amount of heat that you had to put in, the amount of work that you got out changed depending on how you did that. We kind of all stuck the entire time in control volume problems with either one or the other. We had a system that we had Q and work was 0. Or we had a system that we had work and Q was 0. So we kind of stuck in this place where we had only one or the other. We never had both happening. In a control mass problem, it's going to be easier to think about what's happening when we have both going on and how they relate to each other. So that's maybe why we didn't run into stuff like this explicitly. Okay, so at least have these guys written down so that you know what you're aiming for. And like I said, once you get the first one right, then the second ones, you're just plugging in the same thing in your calculator, so it should be pretty easy. If you flip over to the last page, and it looks like we're probably going to get done a few minutes early, which will be good, because we've mostly been done a little bit late in this class. So we can do energy balances like we've done energy balances, our energy balance looks a little bit different now. So don't get them mixed up, but the whole process by which we do them is exactly the same. We can do other types of things like other processes. We did a couple different ones, like a constant pressure, constant volume, pressure and volume both changing. But we can also do things like an adiabatic reversible process. If we did an adiabatic reversible process, Q equals 0, reversible, that means that delta S is 0 for a control volume. The same thing, the exact same process for a control mass. So it's going to look exactly, not exactly, but it's going to look the same. It's going to feel the same. So we'll do one quick example just to reassure ourselves that we already know how to do this. If we have, if we are neglecting kinetic energy and potential energy, and we have an adiabatic process, that means that, right, if we have, this is an adiabatic, I don't know why that's not working, adiabatic reversible process. That means that delta S is equal to 0, and that's our energy balance. If we look at this specific process where we have steam going from 500 kPa, 350, expanding to a lower pressure of 150. So it's kind of like what our, like, if this were a control volume, this would be like a turbine. We go from high pressure, high temperature, and we expand down to lower pressure. We're going to do kind of the same thing, but we're going to start in a in our piston cylinder. We'll draw it like this. So our starting state is 500 kPa. Our starting temperature is 350. There's steam in there. And we're going to be expanding to this final state. To where we're expanding, so we'll show a bigger volume. Okay, and then our final state is P2 equals 100 kPa. Then, so those are our states. Our path here is Q equals 0 and reversible. Okay, Q equals 0, reversible. That means that we know that that S2 is equal to S1. So whatever S1 happens to be, we know S2 must be the same thing. Delta S is equal to 0. Yeah.
So where did the Q equals 0 come from? From up above? Like so that
Right there.
Yeah. Right now it says delta S equals 0. That implies that.
So the process is adiabatic right there. So in the problem statement, we're told that it's an adiabatic process. Adiabatic, this is Q equals 0. So we're told it's adiabatic and reversible. Those are kind of our two key words that we're looking for. Okay, so we can look up, because we know two things, we can look up everything. So we can look up the things that we want. So we can look up that S1 at 500 kPa and 350 C. S1 is equal to 7.6328 kilojoules per kilogram Kelvin. Again, I could plug this into Cat3, but I trust you know how to do that. Then S2 is equal to S1. So our internal energy, U2, is going to be at 100 kPa and 7.6328 kilojoules per kilogram Kelvin. Again, if we look this up, that would be U2 would be 2589.4 kilojoules per kilogram. I didn't write this, I probably should have. So S1 was 7.6328. And U1, again, if we look up S1, we would look up U1 the same way. This was 82.59 kilojoules per kilogram. Okay, so we first look up, we say delta S is equal to 0. That tells us something about the path. That tells us the second piece of information that we need to look up now internal energy instead of enthalpy. Normally we would have looked up enthalpy values. We're going to look up U values. Then our energy balance is delta U equals minus, well, is Q minus W. Q was equal to 0 because we were told. So delta U would be 2589.4 minus 2882.59 equals minus W. I'm running out of room, but we would get W 293.2 kilojoules per kilogram.
Why can't we use the other, like the way that we did before? Like using the pressure in the bottom?
We could.
Oh.
So we could use the equation that we did before. The challenge is we would have to solve, let's, I guess, come back down over here. To use work, the integral from 1 to 2 of, remember what it was? It was P dV. We could 100% use that. This equation works. The only way to use that, though, is to know, right, pressure is now changing. We have to know how pressure is changing. So we have to know how P changes as a function of volume. So we are changing both pressure and volume. So as it's expanding, our pressure is going down and our volume is going up. So we have to know how those two things are related to be able to actually do the integral. Spoiler alert, we kind of do. The way that you guys would start and the way that we'll talk about, at least some of the initial part, we'll talk about it more. I'll actually do problems more later, but we could use something like the ideal gas law, right? ideal gas law explains how pressure and volume and temperature are related for gases, for ideal gases. So in the kind of the extra videos for this week, we're going to do ideal gas law, and we'll do kind of the most basic version of a real gas law, like what do real gas properties look like, and how are they different from ideal gases. So we'll do both of those, but we could use something like the ideal gas law to be able to solve this equation, and we should get the same answer both ways. Question 2, again, how would we do this before? Well, if the process above is irreversible with the device efficiency of 75%, we would first solve for the ideal work. We just did that, 293. Then we would use, right, the efficiency of the piston is work real over work ideal. So the work real is equal to efficiency times ideal equal to 0.75 times 293.2 kilojoules per kilogram. So we could find the real work would be 185.6 kilojoules per kilogram. Okay, and then again, we could go and we could find what the real final state is by going back and doing a new energy balance using this, our previous U. So real final state would be, right, delta U equals minus W. So U2 real minus U1 equals minus W real. And we could find the real U2 real equals 25 2537.9. So we're not asked to do that in this specific problem, but we could, and we would do it the same way that we did for a control volume. Okay, so hopefully this feels really familiar. Right, stuff that we just did on our last exam. We're just redoing it. We've changed things around enough to make it confusing, but not too much. So hopefully it's not too confusing. Hopefully we haven't changed things too much. Liz brings up a really good point that, right, there are different ways that we can do the same problem. We can do, right, energy balances work. Those are, I mean, not use the word work. Energy balances are true, and, you know, an equation like this is also true. That equation, though, only is applicable to ideal systems, only to reversible processes. Whereas energy balances doesn't matter if it's ideal, if it's real, if it's, you know, if it's anything. If it's happening, it has to obey an energy balance. Whereas some of these more specific equations, like this one for work, it has to be reversible. So we will end there, at least a couple minutes early today. As I said, there are 2 videos for this week. Both use, or I guess the second one uses the front and back sheet that I handed out, so have that. And we'll also use that just for reference, so I just wanted to give you that printed out. If you lose it, it's on Moodle. But that's what's going on. So kind of a normal week where we have like some videos, watch those first, then a participation thing, kind kind of just practicing reading that chart to make sure that you can read it correctly, and then a homework for next week. So that's what's going on this week in thermo, this week, week number 10.